Hello again. This is Roger Koch Barr for the Bioelectricity course. We are in week 3, and today we talk about the simulation of active tissue. You will enjoy this. I'm sure you will. So the active simulation is done just like the passive simulation. Everything is the same, except that the membrane resistance corresponds to active tissue rather than passive tissue. The sequence of steps, however, going through is the same basic sequence that was done before. Essentially, over and over, we use this equation. We insert a dt. Normally that's kept fixed. So here let's say that's 1 microsecond. And in that 1 microsecond, we compute a change in Vm. Now with the new Vm, we do the same process all over again. Everything will be exactly the same, except that Vm will now have been modified so that the process accumulates. Each time you go around the cycle, it computes a new change in Vm. You modify Vm, then you go around the cycle again, over and over and over and over, for however long you would like to. So if the simulation goes on for a millisecond, that means it's gone around this cycle 1,000 times, accumulated a millisecond's worth of results through a series of 1 microsecond steps. Now let's look at what happens. Is it ever different? So the passive stimulation, just to remind you, has a stimulus. That's just this pulse, 400 microseconds long. And in the active simulation, it is just exactly the same. The stimulus is again this pulse, 400 microseconds long, the very same amplitude. If we now focus on the response during the stimulus, you recall that with the passive stimulation, the curve of transmembrane potential versus time goes up almost in a straight line. And when we look at the active tissue does largely the same thing. The slope may be a little bit higher, however, so things are not quite exactly the same thing, but very close. But now, let's look at what happens when the stimulus is over. When the stimulus is over, the transmembrane voltage in the passive tissue declines, and it will over time gradually go back to the baseline in an exponential fashion. In active tissue, that just does not happen. What happens is at the end of the stimulus, there's this little resting period, and then the potential goes up and up and up. It's just totally different. And that's why I put this asterisk here, the star here, to bring your attention to the fact that when the stimulus is over, active tissue is off and running and doing its own thing. If we now look at the same graph, but on a different time scale, so now it extends out to 6,000 microseconds, or in other words, to 6 milliseconds. And it extends up to a Vm of 100, meaning 100 millivolts off the baseline. And we have that both on the passive curve and on the active curve, so they correspond. First, let's look at the stimulus. The stimulus down here is exactly the same, 400 microseconds long, same amplitude. It does just what we said before on the passive side, bumps up a little bit during the stimulus, and then comes right on back down to the baseline. That's just the response of a piece of plastic. That's just the response of a piece of cloth. That's the response of any ordinary material. You put in the pulse, and it then gradually charges whatever capacitance there is, but that capacitance discharges during this interval. Now, on the other hand, if we look at the active tissue bumps up during the stimulus, just that little bit, just a little bit shown by this green line. That's all that happens. And then what happens? Then what happens is the active tissue takes off on its own, and here it goes. Well, just going up slowly, 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 and then whoom, whoom, it goes way, way up, way, way up. Over 100 millivolts off of the baseline. You can see that over here, I had to bring the whole trace down by 10%. Just move the whole entire trace down so that on a 100 millivolt scale, it could all fit on the scale. So, I mean, it really goes up there by 100 millivolts or so. That's more than 10 times the amount that was the displacement in the passive tissue. Now, look what else happens in the active tissue. It takes a long, 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 long time to come back down. And then when it does, wow, it's down here even below here. It's even below there. It comes back down to zero and goes past it. Oh, wowzer. If we look at the curve here, undistorted by my earlier marks, you'd say, look, here's where it is when it starts. Here's where it is when it ends. It actually goes negative for a while. So it goes up, way up. Then it comes down, goes up, comes down, and even plunges all the way down underneath the baseline. Now, our graph is not long enough at 6 milliseconds to show it getting back to the baseline level, but eventually it'll come back. It'll take about 10 or 15 milliseconds, but it'll get back to the baseline, but very, very slowly. So I put a big star by this. You can see what happens. If we are going to use analogies here, we could say over here on the left, what happened is I lit a match. I struck a match, and after a while it went out. Over here I struck a match, and it started a huge raging fire. And this whole entire active process, which is called an action potential because there's a lot of action in it, the action potential occurs thereafter. So if I just say it in words, there's a difference during the stimulus, but in this case it's a small difference. But there is a huge, huge, huge difference in what happens after the stimulus is over. Some of my faculty colleagues work on ancient manuscripts, and they tell me that in ancient manuscripts, emphasis was given by repeating the word. So if you fell into a pit, that was a little pit. If you fell into a pit, that was a really deep pit. Well, here I'm saying there's a huge, huge, huge difference, and through repetition saying, it's just different. Once it gets going, it does its own thing, and it's entirely different than before. Let's just think about how it's different. It's different because it's bigger, maybe 10 times the size, and it's different because it goes on for a long time. The difference is not just something that happens for a few microseconds. It continues and continues and continues for thousands of microseconds before it settles back down again. So to restate the striking the match analogy, in the passive case, I struck my match. The match flamed and there was a displacement in Vm, but it gradually died away. With active tissue, it's like I strike a match and wave it over a puddle of gasoline. Boom! That's what happens to the puddle. I put the match out there as the ignition source, and boom! I've got a big flame that results. I certainly better not hold that match in my hand. I can hold it on a long pole if I'm actually going to hold it over a puddle of gasoline, because it's going to go boom and make a big flame. So with that observation, and looking at this tree behind Orange Church in Orange County, North Carolina, near to our campus, we will end this segment and think this over and come back again shortly. Thank you for watching.